Hello everyone. We will now begin our lectures on Chapter 9, which is on conic sections and analytic geometry. We will learn about the different shapes that can be obtained from a conic section. We'll start with the ellipse and then go on to the hyperbola and then the parabola. But what are conic sections? If we take a figure shaped as a cone and slice through it at different angles, we will get different shapes. A circle is obtained if a cone is sliced flat across. Depending on the angle at which the cone is sliced, we can get the other shapes of the ellipse, the hyperbola, and the parabola. So in this series, we will learn the mathematics, the properties of each of these shapes, and also their applications in the real world. In this lecture, we will focus exclusively on ellipses. We will learn how to graph ellipses which are centered at the origin of a rectangular coordinate plane. We will learn about the equation of ellipses in standard form, and then we'll talk about ellipses which are not centered at the origin. That means transformation of ellipses and their graphs, and then finally solve applied problems involving ellipses. We will begin by defining what an ellipse is, and then we will look into the properties that make a particular figure an ellipse. I will read through the definition given here and then I will try to explain. It says an ellipse is the set of all points P in a plane, the sum of whose distances from two fixed points F1 and F2 is constant. Constant meaning they are the same. These two fixed points are called the foci, which is the plural of the word focus. The midpoint of the segment connecting the foci is the center of the ellipse. On the right-hand side, we see an oval-shaped figure, and within this figure there are two points labeled F1 and F2. Each of these points is called the focus, and together they are known as the foci. Now, the speciality is that if you take any point on the circumference of this figure and connect the point with each of these foci, then the sum of their distances, see over here in the definition, it says the sum of whose distances from these two fixed points F1 and F2 would be the same for any point on the circumference of this ellipse. So that is the special property. In other words, the sum of the distance from F1 to this P here, let's just label them as P1 and P2, each of these points. The sum of the distance from F1 to P1 and F2 to P1 will be the same as the sum of the distance between F1 and P2 and F2 and P2. All right. If you take any other point on the other side of the ellipse, maybe this point here, and do the same, connect the point from F1 to F2. So let's call this P3. So if you draw lines from these foci to that 2-point P3, sum up the distances, that value will be the same as whatever we got for the distance between F1 P1 plus F2 P1 or F1 P2 plus F2 P2. So that is the special property of an ellipse. The sum of the distance from two fixed points to any point on the circumference of the ellipse would be the same. Now the other property is that the midpoint of the segment connecting the foci is the center of the ellipse. What that means is if we connect F1 and F2, then the center point of this line, the point midway, exactly midway between F1 and F2 would be the center of the ellipse. This is the center of the ellipse. All right. We will now learn about a few other terminologies of an ellipse. An ellipse can be positioned horizontally or vertically. When the elongated part of the ellipse is positioned vertically, it's a vertical placement of an ellipse. When the elongated part is positioned horizontally, then it's known as the horizontal elongation of an ellipse. The foci in any ellipse is always located on the elongated part of the ellipse. Now, the line segment passing through the foci and extending all the way to both ends of the ellipse is known as the major axis. Therefore, this dashed line extending from one end of the ellipse, passing through the foci, through the center, all the way to the other end of the ellipse is known as the major axis. In other words, the longer part, the longer length is known as the major axis. The center is always located midway between the two foci, and each of these focus is equidistant from the vertex. The vertex is the point on the circumference of the ellipse. It's the end point on the circumference of the ellipse of the major axis. Now, this other dashed line that crosses the major axis at right angles, perpendicularly passing through the center, is known as the minor axis of the ellipse. So let's read through the description here. An ellipse can be elongated in any direction, so direction meaning either horizontally or vertically. The line through the foci intersects the ellipse at 2 points, and each of these points individually is known as the vertex. Together they are known as vertices. The line segment that joins the vertices, this line passing through the foci, through the center, and terminating at either end of the ellipse is known as the major axis. The midpoint of the major axis is, of course, the center of the ellipse, and the line segment, the shorter line, whose endpoints are also on the ellipse, and that is perpendicular to the major axis. In other words, it crosses or intersects the major axis at right angles, is called the minor axis of the ellipse. So always keep in mind that the major axis will have a longer length, a length which is greater than the minor axis. Minor axis has a shorter length. The major axis will always have a longer length. The foci would be located on the major axis always, regardless of the positioning of the ellipse, vertical position or horizontal position. The center point of the ellipse is midway between the two foci. All right? We will now look at the equations of an ellipse in standard form. Now there'll be two equations in standard form depending on how the ellipse is positioned. If it is horizontally positioned, the standard form of the equation is x squared divided by a squared plus y squared divided by b squared equals 1. If the positioning is vertical, then the equation is x squared divided by b squared plus y squared divided by a squared equals 1. The forms are pretty much the same, except that in the horizontal positioning, b squared is aligned with y squared. In the vertical positioning, a squared is aligned with y squared. So it's just that a squared and b squared switch position based on the positioning of the ellipse. On the right hand side, we always have a 1 in the standard form of the equation. But what are A and B? For that, let's look at the graphs given below. the horizontal and the vertical ellipse. We said previously that the foci will always be located on the major axis. In a horizontal positioning, the major axis will be along the x-axis, along the horizontal axis. Now this ellipse has its center point at the origin of the xy coordinate plane. It will have its center at 0, 0. The foci will be along the x-axis in horizontal positioning, and they have given the coordinates of each of these foci at -c, 0 on the left-hand side and +c, 0 on the right-hand side. Now, -a, 0, which is one of the vertices of the ellipse, is a point on the left-hand side. So the coordinates of the left-hand side vertex is -a, 0. It's the end point along the major axis on the ellipse. On the right-hand side vertex, the coordinates are a, 0. So in other words, a represents the x-coordinate of the vertices of the ellipse. The vertices always lie along the major axis. The minor axis, which is vertical, which runs vertically in the horizontal positioning of an ellipse, are 0, b on the upper end and 0, -b on the lower end of the ellipse. So A represents the end points of the major axis, also known as the vertices, and B represents the end points of the minor axis. And in the equation for a horizontally placed ellipse, A is aligned with x and B is aligned with y. As far as the vertically elongated ellipse is concerned, again, foci will always be along the major axis, and in a vertical placement, the major axis will also be positioned vertically. The coordinates of the foci are marked as 0, c and 0, -c, and the vertices are 0, a and 0, -a on the lower end of the major axis. On the minor axis, which now runs horizontally, the endpoints are -b, 0 and +b, 0. All right, so that's what A and B represent. A are points along the major axis, B represents points along the minor axis. So we have to memorize each of these standard forms of the equations of an ellipse. To continue with the equations of an ellipse in standard form, the vertices are always on the major axis, A units from the center, given that it's positioned around the center point of 0, 0. The foci are always on the major axis, and we denote that as -c and +c on either end. Therefore, it's C units from the center point. For both equations, b squared will be equal to a squared minus c squared, and equivalently, c squared will be equal to a squared minus b squared. Let's work on an example of graphing an ellipse which is centered at the origin using the equations in standard forms of the ellipse that we just learned about. It says here, graph and locate the foci of the equation 16x squared plus 9y squared equal to 144. Now, this equation is not in the standard form of an ellipse. Therefore, we first have to convert it to the standard form. Recall that in the standard form, the right-hand side of the equation is always equal to 1. Therefore, our task will be first to change the right-hand side to a 1. How can we do that? Divide all the terms of the equation on both sides by 144. So that's the first step. It says express the equation in standard form. We do that by dividing all the terms of the equation by 144. Why did we choose 144? Because we want to make the right-hand side equal to 1. Since on the right-hand side we have 144, if we divide that by 144, we will get a 1 on the right-hand side. However, we have to do the same thing to all the terms on either side of the equal sign. Therefore, 16x squared divided by 144 plus 9y squared divided by 144 equals 144 divided by 144. And when we do that, we obtain x squared divided by 9. A 16 and 144 will divide. 144 divided by 16 is 9. That's how we ended up with x squared divided by 9. 9 and 144, they would divide. So 144 divided by 9 is 16, and we end up with y squared divided by 16. And on the other side, 144 divided by 144 will give us a 1. We end up with x squared divided by 9 divided by 9 plus y squared divided by 16 equals 1. Now we got our equation in standard form. Now recall that we have 9 below x squared, and that would represent b, and 16 would represent a. Why? Because a is always on the major axis. Therefore, the longer value in the denominator will always represent a, and the shorter value will represent b. So find the vertices. That's the first step after putting it in standard form. Because the denominator of y squared is greater, it'll be the major axis, and a will always be along the major axis. A represents the vertices. So because it's greater, we will choose the greater value as a. Therefore, the major axis for this particular equation is vertical. So x squared equals 16. Therefore, a will be equal to plus minus 4. So the coordinates of the vertices would be at negative 4, 0. Now, if this is a vertical positioning, then it'll be 0, negative 4 and 0, positive 4. We will now work on an example of graphing an ellipse which is centered at the origin. The equation given to us is 16x squared plus 9y squared equals 144. We will go through the steps of graphing the ellipse, and also we will locate the foci point. Recall that the foci of the ellipse is determined by the value of c, negative c, 0, and c, 0 if it is horizontally positioned, and it's 0, negative c and 0, c if it is vertically positioned. We, however, do not know at this point whether the ellipse that we are going to graph is horizontally positioned or vertically. Now, looking at the equation, it is in no way given to us in the standard form. The standard form of the equation of an ellipse is x squared divided by a squared plus y squared divided by b squared equals 1. The right-hand side is always equal to 1. And this is the equation if it is horizontally positioned. For a vertically positioned ellipse, the a and b switch terms, right? So let's start with the horizontal form of the ellipse, because the first step is to rewrite the given equation in standard form. So somehow we have to make the right hand side equal to 1. In order to do that, we will end up dividing all the terms in the equation by 144. That's going to be the first step in our process. Therefore, in order to graph the equation, we will begin by expressing the equation in standard form, which is x squared divided by a squared plus y squared divided by b squared equal to 1. We have to have the terms with a denominator on the left-hand side, and on the right-hand side we must have a 1. That's the standard form of the equation. They have divided all the terms by 144, because whatever you do to one side of the equation, you must do the same to the other side of the equation as well. correct? That's the rule of any equation. And when we do that, 144 divided by 144 is of course equal to 1. Now 16 and 144 will divide. So we will end up with 144 divided by 16 gives us 9, right? So we'll end up with x squared divided by 9 for the first term, and 144 divided by 9 gives us 16. We will end up with y squared divided by 16 for the second term, and then we have equal to 1 on the right hand side. Now, once we have it in standard form, we have to identify which is A and which is B. A always are points along the major axis. Therefore, its length will always be greater than B. Now over here we have 16 below the y squared. The 16 is greater than 9. Therefore, that will be A squared. All right. So 16 will be A squared and B squared will have a value of 9. Therefore, this will be x squared divided by b squared and y squared divided by a squared, where b squared has a value of 9 and a squared has a value of 16. Therefore, this is a vertically positioned ellipse. It's of the form x squared divided by b squared plus y squared divided by a squared equal to 1. Now, once we got that, we can identify the values of the vertices. Because the denominator of y squared is greater than the denominator of x squared, the major axis is vertical. It's a vertically positioned ellipse. We can go ahead and find the value of the vertices. A represents the vertices of the ellipse, which is always located along the major axis. Solve for A here. X squared equals 16. Therefore, A will be equal to, just take the square root. This should actually be A squared. I'm sorry. Let's correct this. It's not x squared. It's actually A squared. So A squared equals 16. Therefore, A will have values plus minus 4. The vertices would be 0, negative 4 and 0, 4 because it is vertically positioned. All right. So we found the vertices. The next step is to find the values of b squared, correct? So let's go on to the next slide to go through the next steps to graph the equation. Now we will find the endpoints of the minor axis, which would run horizontally if it is a vertically positioned ellipse. The endpoints of the minor axis will be determined by the value of b. We have b squared equals 9. We have to take the square root of both sides to find the value of b. That would be plus minus 3. Therefore, the endpoints of the minor axis would be at 0, negative 3 and 0, 3. Again, the minor axis is positioned horizontally. Finally, we will find the foci of the ellipse. That means we have to find the value of c. The formula for that is c squared equals a squared minus b squared. Now note, this is not the same as the Pythagorean formula. In the Pythagorean formula, it was c squared equals a squared plus b squared. This is different. This is c squared equals a squared minus b squared. Therefore, c squared equals a squared had a value of 16, b squared had a value of 9. 16 minus 9 is equal to 7. So taking the square root of both sides, we get c equals plus minus square root over 7. Therefore, the foci would be located at 0, negative square root over 7 and 0, square root over 7. Now that we have found the key points of our ellipse, as well as we know that the major axis is positioned vertically, the vertices are at 0, negative 4 and 0, 4. The endpoints of the minor axis are at negative 3, 0 and positive 3, 0. The foci are at 0, negative square root over 7 and 0, square root over 7. We have the graph of the ellipse using all the key points that we found. position vertically here. We will now go through another example of a problem on an ellipse where we have to find the equation of an ellipse given the coordinates of its foci and its vertices. Now recall that both the foci and the vertices are points on the major axis of the ellipse. The question here says, find the standard form of the equation of an ellipse with foci at -2, 0 and 2, 0 and vertices at -3, 0 and 3, 0. Remember that the foci is represented by the letter C. So we have -C, 0, which -2, 0 would correspond to, and C, 0 would represent the coordinates of the other focus on the ellipse. The vertices are represented by the variable a. Therefore, a would be -3 on one side, so -a, 0, and the other vertex would be a, 0. So we have the values of c and a given to us. We have to find the value of b, because the standard form of the equation is x squared divided by a squared plus y squared divided by b squared equals 1. We have to find values of a and b in this equation. 1 is a constant and x and y will remain as variables. We have been given the value of a. We know that's going to be 3 squared here. It'll become 9. A squared will have a value of 9, but we have to find the value of b. Now, in order to find the value of b, we will have to make use of the values of c given to us. So let's go through the solution step by step. It says here, because the foci has coordinates -2, 0 and 2, 0, and they are located on the x-axis, therefore the major axis is horizontal. Now, how does the coordinates of the foci tell us it's going to be a horizontal axis? Here we see C is the first coordinate in each of these ordered pairs, right? It's -2, 0 and 2, 0. If it were a vertical major axis, then we would have it as 0, -2 and 0, +2. That's how the foci would be represented. However, the coordinates are -2, 0 and 2, 0. The position of C in these ordered pairs tell us that the major axis here is horizontal. All right. So because the foci has coordinates -2, 0 and 2, 0, they are located on the x-axis and therefore the major axis is horizontal. The center of the ellipse is midway between the foci, therefore it will be located at the origin at 0, 0, and the standard form of the equation is x squared divided by a squared plus y squared divided by b squared equals 1. Now, the distance from the center, the point of origin 0, 0 to either vertex is -3, 0 and 3, 0. Therefore, the distance is 3 from the origin to each of the vertex points. The distance is 3. The coordinate would be -3 on the left-hand side and +3 on the right-hand side, but the distance from the origin of both the vertex would be the absolute value of 3, which is 3. Therefore, A equals 3. Therefore, like I said, a squared will end up being 9. Let's find the value of b squared now. For that, we will be going to the next slide to complete this problem. We will now find the value of b squared and complete the problem. We were given the coordinates of each of the focus points of the ellipse. One was at -2, 0 and the other one at 2, 0. Therefore, the distance from the point of origin to each of the focus points would be 2 units, correct? So it says here the distance from the center, which is at 0, 0 to either focus is at -2, 0 or 2, 0, which gives us a distance of 2 units, c equals 2, and we have to use the formula c squared equals a squared minus b squared to solve for b. We have the value of c now, which is 2. We also know the value of a is 3. All we need to do is plug in those values into the formula, which is c squared equals a squared minus b squared, and solve for b squared. Again, to remind you, this is different from the Pythagorean formula. Pythagorean formula has a plus between a squared and b squared. This has a minus in it. All right. So when we solve for b squared, the equation will be b squared equals a squared minus c squared. Plug in the values of a and c. We will have b squared equals 3 squared minus 2 squared, which is 9 minus 4. Therefore, b squared will be equal to 5. We can stop at that. We do not need to find the value of b because we need the value of b squared really to form our equation, correct? So now we can finish off this equation as x squared divided by 9. 9 being the value of a squared, plus y squared divided by 5, which is the value of b squared. The other side is a constant value of 1. Right? So at this point, we have completed the problem. The equation for this given problem, which has focus points at -2, 0 and +2, 0, and coordinates of the vertices being -3, 0 and +3, 0, we'll have an equation x squared divided by 9 plus y squared divided by 5 equal to 1. We will now consider equations of an ellipse which are not centered at the origin at 0, 0. Instead, they may be centered anywhere on the rectangular coordinate plane. The equation in standard form in those cases would be, for the horizontally positioned ellipse, it would be x minus h whole squared divided by a squared plus y minus k whole squared divided by b squared equals 1. The position of the center of that ellipse would depend on the values of h and k. The coordinates of the center would be h, k. If the center position shifts from the origin from 0, 0, then the major axis will also shift. It will be parallel to the x-axis. The vertices would be at h minus a, k and h plus a, k. If the ellipse is vertically positioned, then the equation will be x minus h whole squared divided by b squared plus y minus k whole squared divided by a squared equals 1. Again, the center would be determined by the values of h, k. In fact, the center would have its coordinates at h, k, and the major axis would be parallel to the y-axis in that case. The vertices would be located at h, k minus a and h, k plus a. All right? So we will work through some examples where we will have to draw the graph of an equation which is really a translation where the center point will not be at 0, 0. It'll be at a different location based on the value of h and k. We will now work on an example to graph an ellipse which is centered at h, k. As you can see, the equation given to us is x plus 1 whole squared divided by 9 plus y minus 2 whole squared divided by 4 is equal to 1. What was the standard form of the equation? It was x minus h whole squared divided by a squared plus y minus k whole squared divided by b squared equal to 1. We have to find the values of h and k correctly, and that will tell us where the center of the ellipse will be located. It's going to be a transformation of the ellipse located at the origin. So here we have x plus 1 whole squared divided by 9. We have to rewrite this exactly to match the standard form. When we do that, we will end up with x minus, we have to show the minus because the standard form has a minus in it, but our equation has plus 1. So we extracted the minus sign, therefore we will be left with negative 1. When we extract a minus from a plus, we end up with a negative, correct? So x minus minus 1 is whole squared divided by 9 plus y minus, now it's y minus 2, therefore it will be y minus positive 2 whole squared divided by 4 equals 1. So the value of h always goes with x and k goes with y. So if it's h comma k, that will be negative 1 comma 2, positive 2. So that's where the center of the ellipse will be located. So the solution says here, the standard form is x minus h whole squared over a squared plus y minus k whole squared over b squared equals 1. The value of h is negative 1. The value of k is positive 2, just as we found over here. Thus the center is at negative 1 comma 2. Those are the coordinates of the center point of the ellipse. Since a squared is greater than b squared, it's a horizontally positioned ellipse. The major axis is horizontal and it's also parallel to the x-axis. When the ellipse is centered at 0, 0, the x-axis is also the major axis, correct? The major axis is on the x-axis. However, once the center point shifts from 0, 0, it will no longer be the x-axis, but it will be parallel to the x-axis. So we have a squared equals 9, correct? This is our a squared, and our b squared value will be equal to 4. All right. Now that we have determined the center point of the ellipse using the values of h, k, we can go on to finding the other points of the ellipse. The endpoints of the major axis, that is the vertices of the ellipse, are 3 units right and 3 units left from the center. Now the equation given to us is x plus 1 whole squared divided by 9 plus y minus 2 whole squared divided by 4 equal to 1. We have to find the coordinates of the vertices at both ends of the ellipse. This is a horizontally positioned ellipse. Therefore, the formula to find the vertices are add the value of a, all right? The first denominator is a squared, correct? That represents the vertices on the ellipse, correct? A squared is used to find the coordinates of the vertices of the ellipse, and because this is a transformed ellipse, we will use the value of a. We will add and subtract the value of a from h to determine the coordinates of each of the vertex. So we add 3 units, so we have minus 1 plus 3. Again, how did we get the value 3? By taking the square root of 9, which will represent the value of a. Essentially, the formula is h plus k and h minus k for the other end. So 3 units right is the shift of the vertex, minus 1 plus 3 comma 2. 2 remains the same, k, because this is a horizontally positioned ellipse. And on the left-hand side, it'll be minus 1, minus 3, comma 2. So that will give us the two coordinates, 2, comma 2 and negative 4, comma 2 to represent the coordinates of the vertices. Therefore, the vertices are located at 2, comma 2 and negative 4, comma 2. Now let's find the endpoints of the minor axis. In order to find that, we will need to add and subtract the value of b to k. So the equation again given to us, I've written it out here, is x plus 1 whole squared divided by 9 plus y minus 2 whole squared divided by 4 equals 1. Therefore, we have h equals -1 and k equals +2. To find the endpoints on the minor axis, we have to add and subtract the value of b to k. All right, h remains as is. This time we are finding the endpoints of the minor axis, therefore we only work with k. B squared has a value equal to 4, therefore b will have a value of 2, correct? The endpoint on the minor axis on top would be -1, 2 plus 2, which will give us -1, 4, and 2 units down would give us a point at -1, 2 minus 2, therefore -1, 0. So the endpoints of the minor axis are at -1, 4 and -1, 0. Now that we know the coordinates of the center point of the vertices as well as the endpoints on the minor axis, we can just go about graphing the equation. So here we have our graph given to us, the center point, the vertices, as well as the endpoints of the minor axis. So the center is at -1, 2. The vertices are at 2, 2 and -4, 2. And then the endpoints of the minor axis are at -1, 4 and -1, 0. So let's see how this ellipse, the figure of the ellipse, has transformed. The center point, which was at 0, 0, has now moved to -1, 2. So -1 is here and +2 is here. Therefore, the center point is located right here. If 2 is here, then the center point is -1, 2. So it will be located somewhere here. That's the center point. The vertices are 2, 2. So 2, 2 on the right hand side, 2 and 2. This is 2, 2. And then the other end has -4, 2. So here we have -4, 2. And then the endpoints of the minor axis. The minor axis is the line running vertically through the center point. That's -1, 4. This is -1, 4 and -1, 0 on the other end, on the bottom of the minor axis. Correct? So now we have the graph drawn using the coordinates that we found from the equation, which is the standard form of the transformation of an ellipse.